Hello, so today we're going to be talking about ions and isotopes. We kind of briefly discussed these in the last couple of videos. We're going to dive deeper into what those are today. To kind of start off, we're going to talk about ions. The definition of an ion is it's an electrically charged atom. Now, this overall electrical charge is based on the different number of protons and electrons present within the atom at a particular time. So, if the number of protons is greater than the number of electrons, the overall ion that is formed will have a positive charge. If, vice versa, the number of electrons is greater than the number of protons, then the overall ion will have a negative charge. And then lastly, if the protons are equivalent to electrons, it will have a neutral charge. It will have no charge at all because they're both equivalently positive and negative, and they cancel each other out to form a zero charge. Ions are only created by the gain and loss of electrons. Okay, so the movement of electrons determines what type of ion is produced. Protons will always remain the same within the nucleus. Again, remember, if the number of protons change, then the element that atom represents changes as well. The number of electrons gained or lost by an atom is determined by its position or the element's position on the periodic table. This is true, and we'll dive deeper into what this means when we get to periodic trends and how to read the periodic table. But based on the position of the element on the periodic table, we'll tell if the element is more likely to form a positive ion or a negative ion. Going forward on that, there are two types of ions based off their charges. One is a cation. The cation are what are described as the positively charged ions. They are created by the loss of electrons, which makes sense. If you lose negative charge by the loss of electrons, you're going to become more positively charged. So for example, a common element that will form a cation is calcium. So if it wants to form an ion, it will be most likely to lose 2 electrons to form a +2 calcium ion, or +2 calcium cation. Anions are the exact opposite of cations because anions are negatively charged ions. They are created by the gain of electrons. If you gain more negative charge than you do have positive charge in the nucleus, you become more negative. Therefore, you form a negative ion. An example of an element is nitrogen. If nitrogen is by itself and it wants to form an ion in nature, it is most likely to form an anion of a -3 charge because it wants to gain 3 electrons. An easy way to remember these two different types of ions, there's two kind of pretty distinct ways that I use. If you look at cation, the T looks like a plus, so that's the way I think of it. So if you think of the T as a plus, you can always remember cations are the positively charged ions. Anions a little bit more out there. I think of it as an acronym, AN-ion, which means a negative ion. So if that's the way you want to do it, you really only have to remember one of them. If you can remember a cation is a positive ion, that means anion logically has to be the negative ion. So just be aware of that. Whatever really works for you, but these two are the most common ways and the ways I've developed and how I've remembered them. Okay, then we dive into isotopes. So isotopes are atoms of the same element with a different number of neutrons, which means that all the atoms of the same element have the same number of protons, but they have a different number of neutrons, which means based off what we found in the basics of atomic structure video, they have different mass numbers. Okay, so isotopes can be energetically stable or non-stable. Okay, so the atoms of isotopes can be stable or non-stable. What it means to be a stable isotope means it maintains constant concentrations over time and slowly degenerate, typically smaller in atomic mass. So typically if for example, uranium-238 is highly radioactive. It will break down into different elements based off the particles that it gives away. Again, it will break down into smaller elements as the particles go away. The sun works like that too. The core of the sun is actually a very metallic core, and as it heats up and degenerates based off of this, it'll start giving particles away to form new elements. But those particles go away in the types of light and radiation. Unstable isotopes quickly degenerate at measurable rates to form other isotopes and produce radioactivity. So some isotopes can take millions of years to to degenerate, which makes them stable, or they can take nanoseconds. Okay, so a lot of these synthesized elements that are on the periodic table degrade very, very quickly. So they can give off a lot of radiation, which is the reason why, if you look at periodic table, the bottom two rows that are kind of taken out are the most radioactive because they have very unstable isotopes. Which is the reason why what you'll come to learn is that they're called rare metals, because you can kind of rarely find them in nature on their own. Stuff like that. So they'll typically form larger in atomic mass, because the thing is, unstable isotopes want to be as stable as possible, as quick as possible. So what they'll typically do is that they'll break up into larger chunks to become as stable as quickly as possible. Okay, I know I'm kind of stuttering on my words a little bit, but they will break up into larger masses to become as stable as quickly as possible. Again, radiation is a form of high-energy, fast-moving electromagnetic waves emitted in 3 different types of particles: alpha particles, beta particles, and gamma particles, which you may know as gamma rays, like Incredible Hulk and stuff like that. A radioactive isotope losing one of these particles creates a new type of isotope, and possibly of another element. So these particles have masses which take protons and neutrons away from the nucleus. And since you take protons and neutrons away, it changes that atom into another element. And so as it degrades, it lets these particles off, and it starts becoming a smaller and smaller and smaller mass if need be. So an example is like carbon-14. Carbon-14 is a radioactive element that we use to identify fossils, the age of fossils and stuff like that. But carbon-14 can, since it is a relatively unstable, semi-stable isotope, it will let go of an alpha particle, and it could form a beryllium atom, because it's losing 2 protons in the meantime. Okay, so again, these are the mass numbers. So as a mass number of 14 goes down to 10, which means it loses at least 4 protons or neutrons collectively. But since this carbon atom has 6 protons, the beryllium atom has 4 now. That means that it lost 2. Okay, so this isotopic notation helps us distinguish what radioactivity happens and how these isotopes change as they degrade or form new elements and stuff like that. Okay, so we're going to start diving into the calculations of isotopes and the associated abundances and stuff of isotopes on planet Earth. So fractional abundance is a measurement of how often a particular isotope in nature occurs, expressed without units. It does not have a unit, it's just a fraction or a decimal. Okay, percent abundance is the exact same thing as fractional abundance, but then converted into units of percentage. So it's literally just the fractional abundance times 100%, and you get percent abundance. Okay, so again, percent abundance is equivalent to the fractional abundance, which is just a fraction or a decimal times 100%. The addition of all percent abundances of all isotopes of a particular element must add up to 100%, because you can't have some random isotope missing. So all the isotopes of one particular element, which if it only has 2 isotopes or 12 isotopes, the percentage of each of those isotopes present on planet Earth have to be adding up to 100%. Thus, if you convert it back to fractional abundance, the highest fractional abundance you can have is 1. So again, this is another way you can think of it. The percent abundance of one isotope plus the percent abundance of a second isotope plus the percent abundance of whatever last isotope there is should equal 100%. Same thing with the fractional abundance. Fractional abundance of one isotope plus the fractional abundance of the second plus the fractional abundance of the last isotope should be equivalent to 1. So calculating average atomic mass. So this is actually pretty interesting in how scientists do this. To calculate the average atomic mass of an element, 2 pieces of information must be known. You must know these 2, because if you don't, then you can't perform this calculation. So before you do these calculations, you should always ask yourself, do I have enough information? If you don't, it's probably a different type of problem than you're trying to address. So you need to know the mass in AMUs of each isotope of the particular element. If you don't, then you can't do the calculation accurately. And either the fractional or the percent abundance of each isotope of a particular element. Okay, so if you don't know those 2, you can't calculate the average atomic mass. These 2 bits of info are used to determine the relative masses of each isotope of an element. So since each isotope is a percentage of that total element, okay, because the average atomic mass is going to be the average mass of all the isotopes together to be reported on the periodic table. The percent abundance times its actual mass of that isotope creates what's called a relative mass. It's a mass relative to that particular isotope. So this is kind of weird notation, okay? So the way I said it is that the fractional abundance of that particular isotope, okay, times the mass of that particular isotope, which is n, where n is just the number of the isotope, 1, 2, whatever, is equivalent to the relative mass of that isotope, okay? Another way you can think of it too is that if you take the percent abundance divided by 100%, is the same thing as fractional abundance. So you can do both ones. So if you're given percent abundance or fractional abundance, you can do the exact same calculation. You just need to know that if you're given percent abundance, you need to use this one. If you have fractional abundance, you need to use this one. Okay? So again, I sub m is the isotope's atomic mass at the time in AMUs. And then Rm is the relative mass of that particular isotope. The average atomic mass of the element is the sum of all the relative masses together. So as soon as you calculate the relative masses of each isotope, you can just add them up together to form the atomic or average atomic mass of that particular element. So the average atomic mass of the element that's reported on the periodic table is the sum of the relative mass of the first isotope plus the sum of the relative mass of the second isotope plus the relative mass of the last isotope in the series. So again, Am is the average atomic mass of an element that's reported on the periodic table. So let's do an example. So naturally occurring chlorine is 75.78% 35 Cl. Okay, so it has a mass number of 35, and it has a weight of 34.97 AMU. And 24.22% 37 Cl with a mass number of 37 at 36.97 AMU atomic mass. What is the average atomic mass of chlorine? Well, assuming that these are the only two isotopes that we have, which we can't assume that because what's one way you can do that? Well, you can add these percentages up to 100%. If you add this and this, you'll get 100%, which means 100% of these isotopes are accounted for. You're not missing any. So you can go ahead and do this calculation. Are you given mass and percentages? You're given the percent abundance for each one, and you're given the mass of each isotope as well. So we have that information to perform this calculation. Okay, so the first thing you want to do is calculate the relative mass of each one. So I took the first one, the 35 Cl, and I said, okay, the mass of that isotope times the percent abundance divided by 100%, and I get 26.5 AMUs as a relative mass for that isotope. Do the same thing for the second one. I take 36.97 times the percent abundance divided by 100% equals 8.95 AMUs. And then I can say that the average atomic mass of chlorine is the addition of both of those masses. So I take 26.5 AMUs plus 8.95 AMUs to equal 35.45 AMUs. Well, the next thing you need to ask yourself, how can I check my answer? Well, you can do that on the periodic table. That information is given to you. So if I check the block of chlorine, it says the average atomic mass is 35.452. 35.45 is pretty darn close. Okay, so in regards to significant figures, it might be off by just a little bit, but I would consider this an acceptable answer. Okay, because again, when you're using average atomic masses in calculations, you're going to want to use 2 decimal places. So this is clearly acceptable. So when you do these problems, use the periodic table to check your answer, especially if you're calculating the average atomic mass. And if it turns out your average atomic mass is wrong that you calculated based off what you see on the periodic table for that element, then you need to go back and check your calculations and see what you did wrong. So you may be asked to solve for the atomic mass of one of the isotopes based on a given average atomic mass of an element. So I'm going to give you an example of how this works. Naturally occurring boron is 80.2% B11, mass number of 11, with a mass of 11.009 AMUs. And there's another isotopic form of boron, which we don't know. What must the atomic mass of the second boron isotope be in order to account for the average atomic mass of elemental boron, which is 10.811 AMUs? Okay, so you're given the average atomic mass of boron on the periodic table, which is 10.811 AMUs. And you're given the percent abundance and the mass of the isotope, okay, for the first isotope in the series. Now you're probably asking, well, we don't know the percent abundance of the second one. Well, if we assume that there's only 2 isotopes for boron, Okay, what we can do is that we can say, okay, the percent abundance of the second one has to be 100% minus 80.2, which turns out to be 19.8. So now we know the percent abundance of the second one, which now we have all the information we need to do to perform this calculation. So what you do is you say, okay, the relative mass of the second one is the average atomic mass minus the relative mass of the first isotope. Because we know the average atomic mass is just the addition of both relative masses of the first and second isotope. So you can manipulate the equation to where you can say average atomic mass minus the relative mass of the first one is equivalent to the relative mass of the second one. Okay, which in this case we say that the relative mass is 1.98 AMUs. The next thing we know is that we can bring it back further for our basic equation for relative mass and say, okay, I want to solve for the mass of that second isotope. Okay, so what I say is the relative mass of the second isotope divided by the fractional abundance. Okay, so this is just a percent abundance divided by 100% to get 0.198. Okay, is equivalent to the mass of that second isotope, and it's 10.009. Okay, one way you can check your answer is, like, is it really far off from the isotope, the first isotope mass, or the average atomic mass of the element? It really isn't. I mean, it's 10.811 here and 10.009 here, and then it's off by just a little bit by 1. Okay, remember an AMU is equivalent to 1 proton or neutron, so clearly this is saying that B11 is probably, 1 neutron higher than this mass here. So this is another style of question that you may see on a test or a quiz or anything like that, so be prepared to look into that. And if you have any further questions, please come talk to me. I know there's only so much I can do in these videos, but I'd be more than welcome to work through some problems with you in class. All right, so that's the end of this episode. A little bit longer than the other ones, but clearly for obvious reasons. These calculations are very important. If you have questions about these calculations, please come talk to me. I'd be glad to work through different problems or the same problem in this video and kind of break it down further step by step if you're not mathematically getting that. Again, email me, come talk to me, come visit me in class. Otherwise, thanks for watching this video, and I hope to see you in the next one, and I hope to see you in class.